Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. I'm Drew LaFleur. I'm the CEO and president of Technical Toolboxes. And while we wait for a few more people to log in, just give a little intro to what it is that we're here to talk about today. And welcome you to the latest free webinar event from Technical Toolboxes. So the background on this is we wanted to give you overviews of various topics related to pipeline engineering relevant to today's midstream oil and gas sector. Today we're going to talk about hot tap and in-service welding. Our guest speaker is our subject matter expert, Matt Boring. I say our, it's a contract relationship, but he does help us with training instruction on technical topics, as well as engineering support for software applications. As a company, we are committed to supporting pipeline engineers, and we're always working to share information that helps to increase productivity and reduce costs. Can you go to the next slide? So, as the slide states, we want to have an awareness discussion and talk about some high-level concepts related to hot tap, but we do want to let you know that we do offer technical training on this subject, and we do have software that can help with the assessment and the safe implementation of these work practices. Can you go to the next slide? So the code defined in API 1104 covers hot tapping and welding in in-service pipelines. During that process, burn-through can cause hydrocarbons in the pipeline to escape or ignite during the procedure, leading to spills or injuring workers. After, welded areas may be weakened by hydrogen cracking in heat-affected zones. You need to be able to address these challenges with accurate calculations and minimize your risk. Technical Toolboxes is an authorized agent for PRCI and their Hot Taps Toolbox software. It's a leading industry solution that calculates how to weld on the pressurized live pipelines efficiently and safely. It integrates with Technical Toolbox's integrated data environment in the pipeline hub. So real quick, we're going to take a poll to gauge the audience on kind of experience and how you kind of go about this process right now before we get into the technical discussion. And take just a couple seconds here. You can close this one out and bring up the next question. So do you have any welding experience there? Looks like maybe that one timed out pretty quick. So we'll go straight into the introduction of our speaker today. We go back into presentation mode. So our subject matter expert today is Matt Boring. He's a pipeline welding engineer who works primarily with new pipeline construction, including engineering critical assessments, pipeline rehabilitation, and in-service or hot tap welding. Mr. Boring started his career with EWI and moved to Kiefner & Associates. And more recently, he's joined the Incident Investigation Group at DNVGL, consulting on new construction, fitness for service, pipeline rehabilitation, and integrity. Throughout his career, Matt's been an active participant in code development. He's currently the co-chair of API 1104 Annex B subcommittee, a member of the ASME Section 9 committee, and subgroup on welding qualifications. He's an Ohio registered professional welding engineer, an AWS certified welding engineer, and welding inspector. And with that, I'll turn the floor over to Matt Boring.
Okay, well, hello everybody. Thanks for taking your time out today to listen to this webinar for about an hour. I appreciate it. Yeah, if you want to go to the next slide. What we're going to talk about again is just kind of give an overview of the concerns associated with the in-service welding and how the PRCI Hot Tap Toolbox assists with those concerns. Now, the two primary concerns that most people are concerned about when they're welding onto carbon steel pipelines is the risk of burn through and hydrogen cracking. Now, there are other concerns associated with maybe specific products of the pipelines, maybe if you're welding on ethylene or propylene or something like that, those lines. But generally, the main focus is looking at the risk of burning through and cracking. So the burn through concern really goes back to the safety of the welding crew. You know, when a burn through occurs, you put a hole in the pipe and the product comes out of the pipeline, it can be quite dangerous. Now, that being said, I'm not aware of many instances where a burn through has actually resulted in, say, a fire. It has occurred a couple of times, but it's not as common as someone might expect. But it is a real concern, obviously, to the welders. Hydrogen cracking, that really goes to the integrity of the pipeline. When you're making welds, obviously you don't want any welds to crack. But hydrogen cracking tends to be more of a concern for in-service welds. And again, it goes back to the aspect of there's something in the pipeline cooling the weld faster than it naturally would. And as the welds cool faster, those welds become more brittle. And a brittle weld tends to be highly more crack susceptible than other welds. And I'll get into a little more detail with hydrogen cracking a little bit later. But of these two concerns, in my opinion, I think hydrogen cracking tends to be a little more of a concern. And the reason I think it's a little more of a concern is that it's an unknown risk, right? So you know you might have a risk of cracking, but if you have a crack, you might not know that you have a crack. Yeah, you can inspect these wells. When your inspection might come back clean and you think that you're fine, but in reality, there's a lot of shortcomings to the inspection methods of in-service welds. And it's not so much the inspector or the inspecting technique, it's really just the physics of the inspection method that just are difficult to inspect these types of welds. So you might do an inspection, think your weld's clean, but you might still have cracks because of that unknown aspect of hydrogen cracking. That's why I tend to think it's a little more of a concern. Burn throughs, you know you have a burn through when one occurs. Yes, it's a scary situation, but again, you know you have it so you can fix it, right? So we're going to go to the next slide, please. So when talking about burn through is kind of a little misnomer. In construction welding, there is a defect in construction girth welding. It's called a burn through, and that's what that happens is when a welder is welding the root pass. Depending on the welder technique or maybe the variation in joint, the welding arc force will actually blow the weld pool into the ID of the pipe. So that's typically what a burn through is from a construction standpoint. Now that same term is used for in-service welding also, but for an in-service welding burn through, the welder doesn't actually blow through the pipe wall. What happens is the welder, as he's welding, the area underneath the liquid weld pool is still solid, but it gets really, really hot. When that steel gets hot, steel gets weak. So at some point, that solid piece of steel gets so hot, but it loses all its strength. So it just cannot contain the pressure underneath the weld pool. So what happens is the weld pool, the pressure from the pipeline actually blows out or forces the product out through the weld pool, through that weak steel. So you kind of see that on the bottom left picture that you have the weld pool, and directly underneath the weld pool, you see kind of like a dimple in that pipe wall. And that's just the pipe wall local yielding due to the stress of the pressure and the high temperature property of that steel being a reduced strength. So when a burn through occurs on in-service welding, it's actually what actually happens is a blowout. All right, so you want to go to the next slide? So these are all the factors that are commonly attributed to burn through risk, right? There are a lot of sub factors here, but the three primary ones are really the wall thickness of the pipeline, how the weld is made, and the operating conditions of the pipeline itself. And really, when it comes down to burn through, it's a balancing act. And the balancing act is about how much heat goes in versus how much heat leaves. And this is the same balancing act I'm going to talk about when we talk about hydrogen cracking, but it's from a different perspective. So from the burn through perspective, the balancing act is, hey, we don't want the pipe wall to get so hot that it loses its strength and we burn through. So what we want to do is we want to make sure more heat leaves the weld region than goes into the weld region. So the heat that leaves the weld region, it leaves through the cooling aspects of the pipeline itself, which is the wall thickness, and also what is in the pipeline and how it flows. The heat going into the weld is directly affected by how the welder welds and what electrode he uses. Right? So if a welder welds hot or at a high heat input, he's more likely to burn through a welder than a welder that welds at a lower heat input. Now that's one thing I want to clarify too when we talk about welding heat. From an engineering standpoint and from an in-service welding standpoint, we talk about welding heat input. And what welding heat input is, it's a qualitative value that combines the arc voltage, the welding current, and the travel speed into a single value that kind of gives an idea of how fast or how hot a welding arc is. So the higher the welding heat input, the more energy that welding arc is putting per a given length of weld. Now that's the engineering perspective of welding heat input. Now when you go talk to a welder, when you talk to a welder about welding heat, what that welder normally refers to is just the welding current. Now current is one aspect of welding heat input, but it is only one aspect. So if you talk to a welder and you ask the welder to weld a little hotter, what welders typically do is they'll turn up the current. So they think their welding arc is hotter, which it is in reality. But what then the welder also does, he tends to weld at a faster travel speed. So the welding heat input he's putting in to that weld is actually lower, even though he's welding at a higher current. So when you get the in-service welding applications, you go talk to your in-service welder, it's very important that you clarify what welding heat input means, and that it's not just your welding current. It's a relationship primarily of the current voltage and travel speed, but it's primarily controlled by the current and the travel speed. So typically when you're dealing with in-service welding, you want to control that welding heat input by controlling that welder's welding current range and his travel speed range. So it's two factors, it's just not the current. But from the welder standpoint, he always just refers back to the heat, which is just the welding current. So we go to the next slide. So how do companies historically dealt with burn through risk? Well, one of the more common approaches that companies use is they limit the wall thickness that a welder can weld on. Your typical wall thicknesses are about 188 wall. Some people use 156 wall. But again, wall thickness is just one of the three factors I just talked about. So yes, you can limit wall thickness, but that kind of gives you, it could be both a conservative and a non-conservative approach, meaning you can weld on a thinner wall pipe if you can control the other two factors. So you can weld down the 125 wall pipe if you control how hot the welder welds and maybe control the flow rate of what's going through the pipeline. On the other side, if you have a limit of say 188 wall in your welding manual, a welder might think, well, if I'm welding over 188 wall, I don't have to worry about burning through at all, which is also not the case. Because if the welder welds too hot, you can still burn through pipe over 188 wall. I've seen burn throughs as thick as a 1/4 inch wall. Now it's very rare, and typically the welders might be welding a little hotter when they should have been, but it is possible. But again, it goes back to you have to control all the factors to really determine what is an acceptable risk. Well, that's historically how things have been dealt with. Now, more recently, especially with the development of computers, these thermal analysis models have come to, again, evaluate burn-through risk, but they evaluate it and they compare all the factors at once. And what these models do is they predict what is referred to as the inside surface temperature. And what an inside surface temperature is, it is the temperature directly under the weld pool. The area that was believed to get the hottest from welding at the time the weld is occurring. So if you monitor that location and you keep it below a certain limit, the belief is then you won't have a burn-through risk. And you kind of see that in the picture on the bottom right here. This is a picture of a weld that was made on a pipe, and it did burn through. And you can see directly into the circle, which is called the weld crater, there's a little pinhole of the burn through. So it does occur, again, directly under the weld pool. So the limit that most weld models, including the PRCI model, base their burn through risk on, there's two values, and they're tied to the welding electrode used. The first limit is 1800 degrees F, and that's the maximum inside surface temperature when using a low hydrogen welding electrode. And now if you want to do an in-service weld with a cellulosic electrode, their inside surface temperature limit is 1400 degrees F. The reason for the difference there mainly goes back to the electrode type, and that cellulosic electrodes, they make a welding arc with a lot of hydrogen, and that hydrogen increases the penetration of the weld arc and the weld pool. So because they had that increased penetration, this limit was decided to have an added factor of safety to reduce that inside surface temperature even more. Now, these limits aren't limits that some engineer just picked out of the air. Now, when these thermal analysis models were being developed, and one of the earlier ones was in the late 70s, early 80s, what the engineers did at the time to validate their model was they instrumented pipe spools with thermocouples on the ID of the pipe. And then they drop those spools into a test loop, and they run, whether it's natural gas or propane, through the loop. And then they had the welder weld on the outside of the pipe directly over the thermocouples that were located on the ID of the pipe. And the intent of these tests was to actually put a hole in the pipe. So these engineers intentionally tried to burn through pipe. And the idea was, if we could burn through pipe and we can record the inside surface temperature, we would know at what temperature that pipe wall needs to get before it burns through. And they were successful. So they recorded temperatures around 2300 degrees F when burn-throughs occurred on their setup. So these 1800 F and 1400 F limits that the PRCI model uses has a built-in factor of safety of the actual temperature of the pipe wall of actual burn-throughs of 2300 degrees. So if you run these models and your inside surface temperature is 1805, are you going to burn through at 1805? No, not really. But again, you just have to understand you're reducing some of the factor of safety. Now, I don't know why the engineers picked 500 degrees or 900 degrees, but that's what they did to add that factor of safety. In the PRCI model, what it does do, from the thermal analysis approach, it does predict the inside surface temperature. And I have a couple of screenshots to show where that is when you run the model results. And then next slide. All right, so the other aspect again is hydrogen cracking. Now, again, there's a lot of factors that affect hydrogen cracking, but like burn through risk, there are three primary factors. And those three factors are hydrogen in the weld, a crack susceptible microstructure, and some sort of tensile stress. Now, tensile stress, yes, there are external applied stresses that you have to be worried about, settlement stresses. But one of the big drivers for the tensile stress of in-service welds is just welding residual stress. And you gotta have to accept the fact that you'll have some level of stress. So what most companies do to try to minimize the risk of hydrogen cracking is then address the other two factors, which is hydrogen content and microstructure. Now, the hydrogen that we're worried about, it is atomic hydrogen. So how do we get atomic hydrogen in our weld? It comes mainly from the welding electrode coating. Again, going back to the low hydrogen cellulosic electrodes. Low hydrogen obviously has low hydrogen content, and the cellulosic electrode has a dramatic amount of hydrogen in it. And the hydrogen that comes from the welding electrode gets dissolved or dissociated in the welding arc and gets absorbed by the weld pool. And as the welder travels, that weld pool solidifies. So your weld bead has a certain amount of the fusible hydrogen or atomic hydrogen solidified in the weld bead upon the deposition of that weld. So that's where the hydrogen comes from. The microstructure of the weld is really affected by the material that you're welding and how that weld cools. Now again, you're doing in-service welds, so you can't really control the weld you're making, the material you're welding, because it's again pipeline in the ground. But what you can do from a welding standpoint is control how that weld cools. Again, this goes back to the balancing act between how much heat goes in versus how much heat goes out. So if you have more heat going into the weld, then that weld will cool slower. Welds that cool slower tend to have a non-brittle microstructure. Okay, so anything you could do to have that weld cool slower would allow you to have a less crack susceptible microstructure. Now again, it goes back to the welding heat input perspective. If the more welding heat input you put into the weld pool, the more heat you put into the weld pool, the slower that weld will cool. You need to put more heat into the weld pool because it will counteract the cooling effect of the pipeline. All right. Now the microstructure we're most worried about, we're worried about the weld metal microstructure, but the microstructure we're most worried about is in the heat affected zone. That's the area that tends to be the highest level of hardness. And that's the area that we're most worried about forming this crack susceptible microstructure. You want to go to the next slide, please? So how do we know if we have a crack susceptible microstructure or not? Well, when you qualify welding procedures, you don't really go to evaluate the microstructure of a weld per se. But what you do is you measure the hardness. And the thinking there is crack susceptible microstructures tend to be very hard and very brittle. So if you have a weld heat affected zone that has a high hardness, you suspect that you have a high volume of that microstructure that is crack susceptible. All right, now, how high of a hardness are we talking about? Well, historically, one of the more common values is 350 Vickers. So the thinking back when that limit was really developed was if you have a weld that was over 350 Vickers, that weld is very crack susceptible. And if you have a hardness under 350, then you don't have to worry about cracking. But in this situation, it's similar to burn through risk and wall thickness. Thinking if you draw a limit, if you're over that limit, you're fine. If you're under, you have a concern. Well, from a hardness cracking standpoint, yes, you can have this 350 Vickers hardness limit, but you're allowed to have welds that are higher hardness and still acceptable as long as you control the other factors of hydrogen cracking, which is hydrogen content and stress. So if you go use low hydrogen welding electrodes, again, you can have a weld hardness that is over 350 and it still will not crack. And on the other side, if you make welds with cellulosic electrodes, which has a quite large amount of hydrogen, you would have welds that will have a hardness below 350, and those welds still might crack. Right? So there has been a lot of work in the last 10, 15 years really to looking at what will be considered an acceptable hardness limit for in-service welds, and trying to get away from this idea that 350 Vickers hardness is the limit that we should live and die by. Now, this 350 number is in a lot of the in-service welding qualification codes. So it'll say in API 1104 that if your weld hardness is over 350 Vickers, you need to evaluate your weld for hydrogen cracking. But it's not an acceptance criteria. It's not a go no go acceptance criteria for weld microstructure. It's, hey, if you're over 350, you might want to be worried about cracking. So you want to go to the next slide? This next slide shows what been some of this previous work in the last 10, 15 years that I've looked at evaluating what would be considered an acceptable hardness. Now, as you can see from this graph, this is just one graph of the low hydrogen electrodes. And these curves, they're based on the acceptable hardness limit and the carbon equivalent of the material. So as a carbon equivalent goes across on the horizontal axis, you can see the acceptable hardness limit actually increases. Now these different lines on the graph represent different thicknesses of material. And thicknesses are related to tensile stress by the term of restraint. So the thicker the material, the higher the restraint, so the higher tend to have residual stress and risk of cracking. So the thicker material, the thinner that you have, the thicker material, the less hardness you have, acceptable, and then the higher CE, the higher hardness you have. So as you can see from this, if you're welding on thinner material, less than 375 wall, of a carbon equivalent of say 0.45, with low hydrogen electrodes, your acceptable hardness limit is over 400 degrees, 400 Vickers, which is much higher than the 350 number that has historically been used. Again, on the other side, on the thicker material, the material over 3/4 of an inch down to say carbon equivalent of 0.35, your maximum acceptable hardness is about 325, again, which is less than that 350 value. Right, so how you determine what is your acceptable hardness limit for your in-service weld does vary amongst many factors, and it's up to you to determine what you consider to be an acceptable limit. So you want to go to the next slide? So how does this all play into the PRCI model? Well, the PRCI model allows you to model your in-service welding application, right? So it allows you to model whether it's a gas or liquid line, what type of attachment you're putting on, what's a sleeve or a branch. Need inputs like diameters, wall thicknesses, test temperatures, what the product type is, flow rates and pressures. Then you input your welding heat inputs, whether it's a welding heat input or your welding parameters. And it'll go through the heating and cooling, and it'll predict your inside surface temperature. And then it'll also predict your weld cooling rate. And then from your weld cooling rate, the model uses published algorithms to predict what that weld hardness would be. So this is a typical output screen that you'll see from the PRCI model. So in this case, you have 5 cases on the far left column. Then it has the welding heat inputs. Again, that's the combination of current, voltage, and travel speed to the column right of that. And then it reports out 2 different cooling rates. And then the 5th column over, that's maximum inner temperature. That's your maximum inside surface temperature. So that's the temperature that you have to monitor to predict or mitigate your risk of burning through. The model was set up that for low hydrogen and cellulosic electrodes, if you exceed that 1800 or that 1400 value limit, you have a red asterisk that pops up to say, hey, in this case, at 45 kilojoules an inch, you're going to be risking of burning through. And then the last column is the weld hardness, and that's how the model predicts or mitigates the risk of hydrogen cracking. Again, the model predicts your heat affected zone hardnesses, and then you have to compare that to your acceptable limit to determine whether at that welding heat input, that hardness is acceptable. So this is what a typical output screen looks like. You would like to go to the next slide, please. The model also plots your cooling rate to hardness curves. So if your hardness doesn't show up on that table, you don't have to think you have to go back and rerun the models of different heat inputs to try to get your specific hardness limit that you need. You can go back to these plots. And the plot on the bottom predicts your weld hardness versus cooling rate. And the plot on the top predicts your heat input versus cooling rate. So if you have a specific hardness, say 300 or 400 Vickers, you can use the bottom curve to predict that 400 Vickers what your cooling rate is, and then use that cooling rate on the top curve to predict what that heat input would be. And that would be the heat input that you need to make that weld to hit that hardness exactly. If you weld at a higher heat input, that weld will cool slower, so your hardness will start reducing. So typically from an in-service welding situation, from a cracking perspective, what you have is a minimum welding heat input. So as long as you weld above the minimum welding heat input, you know that that weld will have a less hard microstructure. And on the flip side, from a burn through perspective, if you have a risk of burning through, how you mitigate that risk is applying a maximum welding heat input. So then in those situations, the welder has to be able to maintain his weld above a minimum value and then below a maximum value. So that's what this model is good at doing. It allows you to predict your minimum heat inputs and your maximum heat inputs from a burning through perspective. And then you just have to relate that to your welding procedure and communicate to your welder, hey, you have to weld at this current range, and you have to be within this, say, this travel speed range to be able to comply with the welding heat inputs that the model predicts to be safe for your situation. So that's kind of how the whole model kind of ties into, the mitigating the risk of in-service welding. And that's all I had to talk about. I guess let's go back to you, Drew, to finish up and answer any questions.
All right, thanks, Matt. So we have about 30 minutes left. I only have a couple of minutes worth of talking, but we wanted to make sure that we left plenty of time to answer questions from the various people that have joined online. So if you haven't already, please feel free to type in questions. We will have somebody screening those and asking these for Matt to answer. And if we don't get to all of the questions that come in during this session, we will follow up with each person afterwards to make sure that your question does get answered. That was a great presentation, Matt. Appreciate it, taking the time to walk us through that. Hopefully that conveyed the main concepts of in-service welding to you, helps you have conversations at work and whatnot. And I will be giving a little bit more information about if you'd like to have more training, more exposure in this area, how you might go about getting that. So could you advance? Okay, this is so the key oil and gas industry metrics, they remain at 10-year lows. And the midstream sector is facing losses due to COVID-19. Typically, the midstream lags upstream in the downturns and the upswings by about a year. And so we're coming up on being a year into this. So this is typically the time when it starts to roll into the midstream sector. But the shape of the post-pandemic world and the changes the industry faces are very uncertain. Projects are being delayed and canceled due to community pushback. Net zero initiatives and the growth of the electric vehicle adoption undermine demand. The potential for market collapse means that only the most efficient and productive players are going to survive. So digital tools are essential for pipeline engineers to survive and thrive when better times return, whatever that future looks like. And we at Technical Toolboxes want to help each of you that are on the line be successful in your career and at your company through technical training and through quality software that helps you deliver quality results efficiently. So if you don't mind going to the next slide. So we offer software and training, and our newest platform is an integrated data environment where we're working to release more sophisticated automated workflows and analyses. At this time, Hot Tap is not a part of that, but we do have welding calculations as a part of our pipeline toolbox that may be of interest to some of those on the line. We also offer PDH credit by webinar, and we have a decent size. We have a large pool of SMEs that come from different parts of the industry to do technical training. And Matt is one of those instructors. And he does have a couple of courses coming up in October if folks are interested in that. Evaluating in-service welding burn-through risk and hydrogen cracking. We've got 2 webinars on October 13th. They're an hour and a half to 2 hours apiece. And then API 1104 in-service welding qualifications and the thermal analysis model for hot tap welding will be the following week on October 20th. We are doing all of this virtually during the pandemic. Before this and hopefully afterwards, we have done this as in-person training that is either a 1 day or a day and a half type event. If you go ahead and go to the next slide there. So the PRCI Hot Tap Toolbox, as Matt was saying, is intended to help mitigate some of the risks that you're going to encounter as you weld on in-service pipelines. And it's based on studies that were done, as Matt described, and adheres to the leading practices or recommended practices from various regulatory or professional societies. If you want to go to the next. Like I said, we have a lot of instructors on a lot of topics. Particularly relevant to this webinar is the October 13th and October 20th courses that are coming up on in-service welding taught by Matt Boring. We have another welding related one at the end of September by another SME. Feel free to check out our website if you have further interest in that. To go to the next slide, please. We'll take a quick poll and then we'll get into the Q&A, start going through some of the questions that the audience has submitted. That's probably long enough on this poll. So it looks like most people said skills and development, followed by heat control and burn through. And we'd love to be able to help y'all with all of these. And if you'd like to submit questions on how that can happen, please feel free to do so. This poll question helps us guide future webinars and what topics people would like to hear a talk on. You take a second to take that in. That's probably long enough on this one. Corrosion and integrity management is a top one, and hydro testing. We'll definitely take that under advisement and work to put together a webinar on those topics and meet that need. Thanks for submitting those replies. So, what's the most meaningful next step? Of course, we're going to have Q&A here for 15 to 20 minutes, depending on how many questions are coming in. And then there's other potential next steps where you may be interested in technical training, PDHs, or taking a look at some of the software. But either way, please reach out, contact us with questions, and send us your feedback, including whether or not this was a good use of your time, if you got value out of attending this discussion. So with that, I will turn it over to Joseph Ladner. He is an engineering performance advisor who has been aggregating the questions behind the scenes, and he will ask Matt some of the ones that he's seeing most frequently within that question set. And as I said before, if we don't get to all the questions that have been asked, we will follow up via email and make sure that Matt has a chance to answer your question. Thanks again, Matt.
No problem, guy.
Yeah, thank you, everyone. Hopefully you're able to hear me right now. So we're going to spend the next 15, 20 minutes max going over some questions. To be perfectly transparent with everyone, I've seen a lot of really good questions come through. I think we're at several dozen now, well over 30. So as Drew stated, I just want to reiterate, we're probably not going to be able to get to everyone's question. I'm going to try to maybe combine some together as needed to where we can knock out two birds with one stone here, if any questions. But if we don't get to your question, as Drew reiterated, if any of you have attended our other webinars, we will be following up with you with answers individually if we don't get to your questions. So appreciate it. So kind of going through these here, I got a couple of just high level questions in regards to the software itself that I want to answer. So I see some general questions in regards to how can I find out more information about the software, where can I get more information there, how can I learn more, etc. Well, as Drew stated, we obviously have our training courses. I mean, those are an easy way. We have several SMEs there, with Matt being one of them, and those are coming up. You can go on our website to take a look at those. As far as getting information about what the Hot Tap software does, the PRCI Hot Tap, if you go to our website, there's some information there. You can email info, again, info, I-N-F-O, at technicaltoolboxes.com. We can send you some more information. Again, email myself, Joseph Ladner, or jladner at technicaltoolboxes.com. Happy to take care of you. I've seen some other questions about is how can we take a look at the actual software? Can we see the software, etc. One thing we can offer you there is trials available for that. So if anyone is interested, again, we do compile all the questions together. So if you're interested in a trial of that, how can I take advantage of that for a very short period of time, test it out, see what you think? Please, by all means, just put interested. Again, just put the word interested in the chat bar below. And in the next couple of days, or as soon as we can obviously get with you on some more information or taking a look at a trial of the PRCI Hot Tap program. Again, just put interested on there and we'll get with you. So those are some of the general questions I wanted to cover. And now we're going to get to the technical questions. So this is going to kind of start kicking over to you, Mr. Matt Boring. But the first question I have for you, sir, that I've kind of seen a couple of times in here is, you described the three primary factors associated with reducing hydrogen cracking. In your opinion, what is the most important of these three factors? First question for you.
All right, so of the three, I mean, I would say the most important one is controlling your hydrogen level. By controlling the hydrogen level, you really have a lot of flexibility with how you weld. And what I mean with flexibility is you don't have to put as much control on the welder and his welding technique given the material you're welding. All right, so with low hydrogen electrodes, what it allows you to do is have a weld with a much higher hardness. Now the microstructure, yeah, you can get welds that can still crack under low hydrogen conditions, but you get a lot more window of operability when you're using low hydrogen electrodes. So of those three, that's what I would say. I would say controlling your hydrogen levels, so welding with low hydrogen electrodes, the 7018 H4R rods from a fresh can. Make sure the pipe's clean, rust-free, grease-free, not sweating, no oils or anything like that around. That's really, I think, your first line of defense from a hydrogen cracking risk is using low hydrogen rods.
Okay, perfect. Got another question for you, sir. So is there a wall thickness above which a company would not really be worried about what is in the pipeline?
There it is, but it's not really a hard limit. All right, so generally speaking, because we're talking about how weld cools, right? And the cooling comes from what's in the pipeline and the thickness of the pipe wall. As the pipe wall gets thicker and thicker, the effect of what's in the pipe on how that weld cools drops off lower and lower and lower. So that limit is typically considered to be around 1/2 of an inch. So if you're welding on something thicker than 1/2 of an inch, what's in the pipeline and how it flows isn't really going to affect how that weld's going to cool that much. Now, if you're under 1/2 of an inch, again, once you start increasing flow rate, it'll start cooling, faster and faster. But as the weld thickness gets thinner, what's in the pipeline really dictates how well that cools. So then you can start affecting flow rates and, you know, welding under no flow or a little bit of flow, or controlling the flow rate of the pipeline to help control how the weld cools. But if you're over a half of an inch, what's in that pipeline and how it operates, it really isn't going to affect anything's going to cool.
Okay, perfect. Well, definitely going to try to start going through more of these questions here. Thank you, Matt. So another one that I have is, does pipeline pressure significantly affect burn through? Again, does the pipeline pressure significantly affect the burn through?
Now, that's kind of a little bit of a tricky question. And the reason I say that is, from a model perspective, the answer is no, it doesn't. And the reason it doesn't is, what pressure does within the model is it affects the thermal conductivity properties of the product. So at gases at higher pressure, that liquid natural gas will start acting more like a liquid. So pressures will start cooling the weld faster at higher pressures than at lower pressures. Pressure doesn't really have much of an effect at all on liquids because it doesn't affect the properties of the liquid. Right? Now, historically, people are worried about pressure, and pressure became a big driving factor for the risk of burn through before these thermal analysis models were developed. So before these thermal analysis models were there, engineers were worried about burning through the pipe, so they said, how can we address burn through risk? And what they used is they used typical pipeline design equations like the Barlow equation, and kind of predicted that at a certain wall thickness, what will be a maximum pressure.
Mm-hmm.
So because of that historical reference that a lot of companies have built in their manual, people still cling on to that even to current times when these thermal analysis models are more available. Right. So what I always try to do is, yes, pressure is an input into the model, but I would not control your in-service welding application based on an operating pressure, as long as it's related only to welding. I would put the pressure in there, and when the results come out, that's fine, and that's what I would go with. Now, one reason why pressure is still going to be somewhat related to in-service welding, and will always be, is because oftentimes you're making an in-service weld on a piece of pipe that has damage to it. And a lot of design codes require you, based on what that damage is, to reduce the pressure before you can operate on that pipeline from a safety standpoint, to make sure that damage doesn't rupture while the bell hole's open. That's not a welding related issue. That's the integrity of the pipeline. So if somebody comes to me and says, do I have to drop the pressure if I'm going to do an in-service weld on brand new pipe? My answer is no, you don't have to drop the pressure. You just have to model what it is.
Mm. So Matt, I'm going to kind of piggyback off that one just a second for the risk of burn through. Kind of talking about the how does the pressure affect it. Piggybacking off that, could you explain the factor of safety, greater or smaller, and how that will risk burn through?
I guess I'm not really understanding the question. The factor of safety, greater or smaller, what factor of safety, I guess, are we?
I think it was referencing we'd probably have to go back through the presentation. You might have had a part where you were going through the factor of safeties, greater or smaller, will risk burn through.
Yeah, so the limits that the model uses, the 18 to 1400 limits, have a factor of safety built into it with respect to the 2300 degree limit that the pipe was when burn throughs occurred. So that's just the limit the engineers use, and that has just been adopted by the PRCI model and other computer models to say this is the limit where burn through has to be. You know.
Gotcha.
So I don't know. I mean, because there's a factor of safety there, if you wanted to, as yourself, accept some more risk and have an inside surface temperature maybe slightly over 1800 degrees, again, that's again is accepting that liability. But the model puts the limit at 1800 and 1400. I don't know anybody that really goes in and says, well, I'm just going to run the model, but I'm going to use 2000 and not 1800. You know, if that's the question. But again, you can always go lower. I mean, if you don't want to use 1800, you want to use 1700 and 1600 for low hydrogen rods. That's fine. You're just adding more safety to your situation. But I just want you to, the point of me pointing out there's a factor of safety there. I just didn't want to think that if I weld over 1800, I'm going to burn through. You're not going to. You know, you just had to draw a line somewhere, and that's where they decided to draw the line.
Okay. Next question for you that I kind of have ready to go is, how can we establish and check recommended cooling rate?
You don't really, I guess, check the recommended cooling rate, right? So the model predicts what the cooling rate is, and you just kind of make the leap that at that welding heat input, at that cooling condition, at that operating condition, the weld's going to cool that way. Now there are field checks that you can do. One of them is called, the terminology is called the EWI heat sink capacity check. And what that does is, that's essentially a field check where you would heat a small circle of the pipe up, and you measure the time that small circle of pipe cools from 250 to 100 degrees C. So that would be, say, 10, 12, 13 seconds. And then you could do that for your qualification conditions, and then do that same thing in the field. And as long as, and those two numbers will be qualitative values. So as long as the field weld time is, say, 30 seconds, and your weld procedure qualification time is, 10 seconds, that means your qualification cools faster than your field, so then your field weld won't crack. That's the only way that I could see comparing some sort of cooling rates, but that's not necessarily the cooling rate that's used to predict what the weld hardness is. So we don't really, when you're doing in-service welds, we don't really look at actual weld cooling rates to that level of detail, that granularity. It's more qualitative values. Is you got to make sure your qualification conditions, that weld cools faster than your field. It doesn't necessarily have to mean it has to cool a lot faster, or there's no way to say it has to cool twice as fast or 3 times. It just has to cool faster. And this tool in a model, again, it gives you, that's one way you can do what the model is. You can model your 2 different conditions and compare the cooling rates. But the absolute value is not necessarily as important as the relationship to each other. As long as one is faster than the other, then you're good to go.
Understood. Okay. Compiling some more questions here. Again, as I want to read it to everyone, I think we have about 8 minutes left, so still want to try to get to several other questions. If we don't get to your question, we'll certainly do our best, and we'll follow up with you in the next several days and try to get you an answer. But again, I see some questions in regards to the software itself. If you want to get more information on that, just to kind of make it easy on you, just let us know in the chat bar, or just put interested, and we can get with you on a demo or trial. Next question for you, Matt. Why do we reduce pressure to 500 PSI to avoid burn through?
Like I said before, I wouldn't. I've never heard of an absolute value of 500 PSI to reduce burn through. That one's new to me.
Okay.
And my perspective again is I wouldn't necessarily reduce pressure. Now I know in some situations you might have to reduce pressure to change flow rate, and maybe they reduce pressure to change flow rate so the weld doesn't cool as fast. But I've never heard of an absolute value like 500. The more common value I've heard of a pressure reduction is a reduction of 80% of the operating pressure. But again, that relates back to the integrity of the pipeline, because you're exposing a pipe that has a defect in it. And that doesn't necessarily relate to welding. But yeah, I mean, if the company has a limit of 500 PSI, I would be interested to hear where that comes from. And I would kind of argue against that limit, because again, this PRCI hot tap model and other tools are out there that have been shown to be very safe. And if the model shows that you can weld at a higher pressure, then I absolutely would say that you can weld at a higher pressure.
Gotcha. Got another few for you. Can we do hot tapping for cladded carbon steel?
You can, but I don't know if this model would be able to do that, because they can't model cladding. But I mean, you could do an in-service weld on a clad, say a clad vessel. assuming the clad's on the ID. I'm assuming that's what the situation is describing.
It is.
So, I mean, in-service welding on a cladded vessel, I think, is done quite often in refineries. Obviously not so much in pipelines because, pipelines aren't necessarily cladded pipe unless maybe it's offshore. But yeah, I would say you can do that, but there's other things you need to take into consideration. But from the welding standpoint, I absolutely think you could do that and do that successfully. It's just something that you'd have to think, take a little more care in how you evaluate it. The one thing you'd want to be very cautious about if you're doing an in-service weld, and you said hot tapping. Well, the welding part, yes, but if you're tapping through a vessel that's clad, I mean, that vessel's clad for a reason. So if you're cutting through that and then you have product that's exposed to the carbon steel, you might have bigger problems. So I don't know about cutting through a cladded vessel because of the corrosion that may occur later. But say welding onto a vessel, I think is reasonable. And that's, I guess, one point I forgot to mention earlier because you said hot tap welding. And hot tap welding or hot tapping is typically referred to in-service welding, and they're synonymous, when in reality, it's not really synonymous. I mean, in-service welding is one part of the hot tapping operation. So I would say, yes, you could do some in-service welding on cladded vessels, but I would be cautious about hot tapping or drilling the hole into a cladded vessel.
Okay. Thank you for that, Matt. Got another one for you. This is going to be based on your experience. Based on your experience, sir, what would you say is the flow process most at risk of burn through, liquid or gas?
It'll be gas. And mainly because the liquid just does a much better job at pulling heat away from the pipe. Now, you can get gases at high flow rates that act similar to liquids. But by far, I would say that the highest risk with respect to product is gas lines have a higher risk of burning through just because the gas itself may not cool the weld as fast. But you can burn through both situations, right? Just because it's liquid doesn't mean you're not going to burn through. You still can. But I would say that risks are slightly lower.
Gotcha.
But one thing I want to emphasize, I guess, with liquids too is, I guess, burn through is one aspect of liquids, but oftentimes the product itself has other concerns except burning through. So some refined products might react at elevated temperatures at a given pressure. So in those situations, if you're welding, you might burn through, but you might get the pipe hot enough that product starts a chemical reaction that is adversely going to affect your pipeline. So burn through is one part of it, but when you're dealing with liquids, you also want to look at the actual product itself. And you might think that the limiting heat input might not be for burning through the pipe, but it might rather be to make sure that that product doesn't react at that pressure and temperature. So the model, again, will help you predict an inside surface temperature that could be used to help mitigate that risk of a reaction, but that's something that's going to be beyond just burning through a pipe. So outside the concern of a reaction of the liquid, if you have a benign liquid like crude oil compared to natural gas, yeah, your crude oil would cool the weld faster, so you have less risk of burn through.
Okay. A question for you kind of specifically pertaining to the PRC hot tap program. So how does the program handle the entry of actual welding parameters versus just entering heat input?
The model does both. So the user has an option. So you can put in your current voltage and travel speed, or you can just put in a heat input value. Now the output report, all it does is report the heat input. So if you put in current voltage and travel speed, the model will calculate that heat input, and that heat input value will be the value that's on the output report. But there's other input reports that the model has that I didn't show, but the input reports will give you the current voltage and travel speed. So you have an option to put in either the heat input value or the current voltage and travel speed.
Okay. We'll try to squeeze in one more question since we have roughly 1 minute left. I want to be mindful of everyone's time. So the question is in regards to slow cooling after in-service weld. Is this practice really doing anything given the cooling rates and the time to reach peak hydrogen content in the weld?
When he says slow cooling, I'm going to assume what he means is keeping the weld hot after the weld is completed. Now, based on that assumption I just made, what that keeping the weld hot does, it doesn't affect the microstructure or how much hydrogen is in the weld per se. But what it does do is it increases the diffusion rate of the hydrogen that is in the weld as it goes through the steel. So making a weld and keeping that weld hot makes that hydrogen that is around diffuse out quicker. So what that is really doing is it's reducing the time that you might have to wait for a hydrogen crack to occur, because it's getting the hydrogen out of the area faster. And oftentimes people put this slow cooling or keeping the weld hot perspective added to their procedures because what they want to do is reduce the inspection delay time for hydrogen cracking. So most pipeline codes, when it talks to in-service welding, says that you need to delay your final inspection of in-service welds, say 12 to 24 hours, because they want to make sure that if a hydrogen crack does occur, if you come back and inspect it later, you'll be able to find it. The last thing you want to do is bury a pipe and have a crack occur after the inspection. So that's the reason for the delay times. And people do this, make the weld hot and keep it hot to make sure that the hydrogen that is around gets out of the way. So hopefully they can shorten that delay time to be a little more efficient. Now, if that doesn't answer your question, I might have misunderstood what you meant by slow cooling.
And we can certainly follow up with him, and actually just got a confirmation that it did answer the question. So appreciate that, Matt, and appreciate the question there from that was submitted. Well, we're at 1 minute after, everyone. We'll do our closeout here again. I know there was a number of questions that was not able to get answered. Again, we will follow up with you, and for the ones that are interested in the Hot Tap program, that put interested or like to receive more info, we'll follow up with you too. If you haven't, please just feel free to submit in the question bar or chat bar that you are interested, and we'll certainly make sure to follow up with you, and we'll compile this over the next several days and get it over to Matt and make sure we get answers to your questions. So very much appreciate everyone joining the webinar today. Again, those polls are there for a reason. So we'll be looking over the next several weeks and months to possibly get more out, definitely pertaining to what you all want to see. Again, thank you all for joining. It's been a pleasure. Hopefully you all found benefit out of this and was able to learn a little bit more about in-service welding and hot tapping. And we very much appreciate you and your interest in that. And of course, Technical Toolboxes. Thank you all, and have a great rest of your Wednesday.
Have a good day, guys. Bye.
Bye. Thank you, Matt. Appreciate it, sir.
No problem.